Time travel has been an important part of the world's literary culture for decades now, and has always been the theoretical dream of many.
But the ability of moving forwards and backwards in time has always been thought of as theoretically impossible. But is that really true?
To understand this, first we must look at Einstein's theory of relativity. Einstein stated that no matter where you were in the universe, both space and time were interlinked. That is to say, if there is a distortion in space, there will also be a distortion in time.
He also stated that large bodies of mass, such as the Earth, cause such a distortion in time, an effect that we can feel and call gravity.
So following Einstein's theory, this distortion in space must also cause a distortion in time. That is to say, the greater the force of gravity acting on an object, the slower time will move for it in relation to Earth. This is a point well shown in Christopher Nolan's Interstellar.
An important note to make is that the decrease in the speed of time is relative to Earth. So let us say that there are two people, and one standing on Earth, the other standing on the planet with increased gravity, for clarity we shall call planet X.
So for the person standing on Earth, time will appear to be moving at a normal speed, but if he were to look at planet X, time would appear to be moving much slower.
But for the person standing on planet X, time would also appear to be moving at a normal speed, but if we were to look at Earth, time on Earth would appear to be moving much faster.
This proves that things will only appear to be moving at different speeds relative to the observer. For both people think that their clocks are moving at a normal speed, and that the clock of the other is either moving at a faster or slower speed than normal.
It doesn't take a large amount of change of gravity to affect time. For example, if a clock was placed on top of Mount Everest and one was placed at sea level, the clock at sea level would be 39 hours ahead if it was left for the Earth's entire lifetime.
Light is the only thing that moves at the same speed independently of all other variables. So the person on Earth and the person on planet X will observe light at moving at the same speed. So light is the only constant in the universe.
Now gravity isn't the only thing that can distort time, as shown in the film Interstellar. Again, time seems to change dependent on the velocity of the observer.
As with gravity, the greater magnitude of velocity, the slower time appears to move. This was proved in October 1971 with the Haffel-Keating experiment by physicist Joseph C. Haffel and astronomer Richard E. Keating. Took 12 atomic clocks.
The importance of the clocks being atomic is that they are accurate to the nearest nanosecond.
On board commercial airlines and flew around the world twice. 4 eastwards, 4 westwards and 4 left on the ground.
When the clocks were brought back together, they found that the times no longer agreed, proving that the velocity had distorted the flow of time.
To show this, just watch this video from Professor Brian Cox's lecture on time dilation, which proves this point well. A man is holding a light and moving it up and down. Then he is moved side to side on a trolley. The moving up and down of the light represents it bouncing between two mirrors, and since light is constant, we can use this as a very accurate clock.
From the audience's point of view, the light is moving up and down diagonally, but for the man holding it, it appears to be moving only vertically.
Since light is constant, the light travelling diagonally, i.e. the man moving from side to side, takes longer to travel than the light moving only vertically.
This is when Einstein realised the simple fact, that time must move slower at a greater velocity. This also proves that there is no absolute time. The two parties, the audience and the man, were both looking at the same thing and observing it differently. This shows that time is always relative to the observer and not an independent force always going at the same pace.
We can actually calculate the effect on time due to velocity using the equation time seen by the stationary observer equals time in rest frame over the square root of 1 minus velocity squared over the speed of light in a vacuum squared.
So inputting numbers, time on a ship travelling at 30 million meters per second equals 1 over the square root of 1 minus 30 million squared over 299,800,000,000 squared.
A pretty large calculation, and the answer is
1.005 seconds.
yes. If you're travelling at 30 million meters per second, 0.01% the speed of light, time would move 0.005% slower.
That's not a large difference.
Yes, and considering that the fastest humans have ever gone in space, achieved by the crew of the Apollo 10, is only 11,082 meters per second, it might take some time for humans to develop ships fast enough to make a difference in time.
So travelling forwards in time seems like a pretty simple procedure. Simply enter a gravitational field much greater than Earth's, unadvisable since being in an atmosphere more than 5 times the Earth's gravity could be fatal.
And on the surface of the Sun, which has 28 times Earth gravity, time only moves 66.4 seconds slower per year.
That is also not a lot, but we can't achieve that velocity or the magnitude of gravity. So this really doesn't affect our lives, does it?
Not quite, sometimes it is the smallest details that matter. Imagine that you have a GPS that you bought at a shop for around £100. How does it work?
24 satellites in orbit around the Earth communicating with each other and the Earth to pinpoint your position. What's that got to do with time dilation?
Well, these satellites contain atomic clocks that have a precise time to the nanosecond. That's 1/billionth of a second. Now, these satellites are 20,000 kilometres above the Earth and have an orbital speed of around 14,000 kilometres an hour. So what's going to happen?
Time is going to move differently. What has that got to do with locating you?
As we discussed before, space and time are interlinked, woven around each other. Imagine I was trying to meet you. To do this, I would have to tell you both the place and the time I wanted to meet you. One of these pieces of information would be useless without the other. It is exactly the same for a satellite. To get your location down to 5 to 10 metres, it needs to have a clock accurate to around 20 to 30 nanoseconds. Now, time dilation is going to mean that the satellites are going to tick around 38 nanoseconds faster per day.
Then what would happen?
GPS readings would be wrong after only 2 minutes, and the errors in pinpointing your position would increase by 10 kilometres per day.
So how would they fix that?
Luckily, the satellites are programmed to compensate for the increase in time. So this happening is technically impossible, but scientists had to use the theory of relativity and the time dilation equations to solve this question, showing just how important these equations are.
Therefore, moving forwards in time is not impossible then. If you want to move forward in time on Earth, you go into space and travel at a velocity close to the speed of light for a few years, and when you return, the Earth would have aged more than you have.
Problem is, you'd have to be going very close to the speed of light. As this graph shows, you have to be travelling over 90% the speed of light before the real changes come in. Moving at only 30 million metres per second, after 50 years, you would only have aged a minute and a half less than when you were on Earth. This graph shows that the closer to the speed of light you get, the greater the increase in time dilation. So if you travelled at 99.4% the speed of light for 10 years, 29 years would have passed on Earth, meaning that you would have arrived on Earth in 2034, having only aged 10 years.
So time travelling is technically possible, just not practical. So possible, just not yet.
Yes, this velocity may seem impossible now, but who knows what might happen in the future.
Or you could move to a planet with a much higher gravity than Earth. But for the gravity to be large enough to make a difference, it would also probably kill you.
So again, possible, just not yet.
Yes, this level of gravity may seem impossible to survive, but who knows what humans might invent in the future. So what about moving backwards in time? If the closer we get to the speed of light, the slower we go. So when we go over the speed of light, time will move backwards.
That is a very popular question, inspired by shows such as Star Trek, where time travel was as easy as going down to the shops. But the bottom line is, we don't know because it isn't possible.
You mean not possible yet?
No, I mean completely impossible. Doing that would break every rule in the book of physics. It's like asking what would happen if you went back in time and killed your own grandfather. The answer can't make sense because the question doesn't make sense.
So we can never do that.
No, if you throw one rule of physics out the window, then you have to throw them all out. The whole theory of relativity is based on light being the only constant in the universe, the finite speed. Saying that we went faster than that would break all of that.
But it is a popular speculation. Many scientists do believe that if we could, then travelling back in time would be a high probability.
So travelling forwards in time relative to Earth can be one of man's aspirations, but the truth of the matter is that travelling backwards in time cannot be. So that kind of time dilation is one that we are going to have to leave for the films.
So therefore, moving forward in time is not possible then. If you want to move forward in time on Earth...
No, what? It's not impossible.
Oh.